There's something almost magical about stepping outside on a clear night and looking up at the stars. But what if I told you those tiny pinpricks of light aren't just beautiful, they're ancient messages, carrying secrets from a time before Earth even existed? Every flicker, every glow in the night sky is a cosmic telegram sent across billions of years, and tonight we're going to learn how to read them. This is the story of ancient starlight, the universe's oldest language, and how it's whispering to us about the birth of galaxies, the mysteries of dark matter, and even the very fabric of time itself. Think about the last time you saw a shooting star, a fleeting streak of light that vanished in a heartbeat. Now imagine light so old it's been traveling since the universe was in its infancy, before planets formed, before the first stars ignited. That's what astronomers are capturing when they peer into the depths of space. These beams of ancient starlight aren't just pretty, they're time capsules, holding clues to how everything we know came to be. And the most incredible part, we've only just begun to decode their meaning. So how does light become a messenger? It's not just about brightness or color, it's about the hidden stories etched into every wavelength. When starlight passes through cosmic clouds or bends around distant galaxies, it picks up fingerprints of the universe's history. Scientists use these subtle clues like detectives piecing together a billion-year-old crime scene. By the time we're done, you'll never look at the night sky the same way again. Those aren't just stars above us, they're pages in the universe's oldest diary, and tonight we're going to learn how to read them together. To understand how starlight becomes a cosmic messenger, picture it like a secret code written in invisible ink. Every beam of light that reaches us from distant stars isn't just empty brightness, it's packed with layers of information waiting to be deciphered. The key lies in something called spectroscopy, a tool that splits starlight into its individual colors, much like sunlight passing through a prism creates a rainbow. But here's where it gets fascinating. Those colors aren't just pretty, they're a detailed fingerprint of the star's very essence. Take redshift, for example. When a galaxy races away from us, its light stretches like a cosmic rubber band, shifting toward the red end of the spectrum. This simple color change tells astronomers not just how fast the galaxy is moving, but also how far away it is, giving us a way to map the expanding universe itself. On the other hand, dark lines cutting across that rainbow of light reveal something even more astonishing: the chemical makeup of everything the light has passed through. Imagine starlight as a detective, picking up traces of hydrogen, helium, or even distant cosmic dust as it journeys across space and time. But ancient starlight is the real treasure. These are photons that have traveled for billions of years, carrying snapshots of the universe when it was just a toddler. When we catch this light with powerful telescopes, it's like uncovering a time capsule from the cosmic dark ages before the first galaxies fully formed, when the universe was a swirling soup of raw ingredients. Each faint glimmer holds clues about how stars ignited, how elements were forged, and even how the very fabric of space itself evolved. And here's the mind-blowing part: we're only scratching the surface. The next generation of telescopes, like the James Webb Space Telescope, are designed to catch even fainter whispers of this ancient light, peeling back layers of the universe's history we've never seen before. So the next time you gaze up at the stars, remember, you're not just seeing points of light, you're looking at billions of years of cosmic storytelling, written in a language we're only just beginning to understand. Modern telescopes are more than just powerful lenses, they're time machines, bending the rules of physics to bring us face to face with the universe's earliest moments. Take the Hubble Space Telescope, for example. Floating above Earth's distorting atmosphere, it captures light that's traveled for over 13 billion years, showing us galaxies as they looked when the cosmos was a fraction of its current age. But Hubble's just the beginning. The James Webb Space Telescope, with its gold-plated mirrors and infrared eyes, goes even further. It doesn't just see light, it sees heat, piercing through veils of cosmic dust to spot the first stars flickering to life in what astronomers call the cosmic dawn. Here's how it works. As the universe expands, light from the most distant objects stretches into longer, redder wavelengths, like a cosmic fingerprint smeared across time. Infrared telescopes like Webb are built to catch these stretched-out whispers, photons that have been traveling since the universe was a swirling nursery of raw hydrogen and helium. But it's not just about distance. Every photon carries a story. When starlight passes through clouds of gas or wraps around massive galaxies, it picks up subtle distortions, tiny clues about the invisible scaffolding of dark matter or the fingerprints of newborn elements forged in stellar furnaces. What's truly groundbreaking is how astronomers stitch these faint signals together. By combining observations from Hubble, Webb, and ground-based telescopes, they assemble a cosmic scrapbook, page by page. One image might show a galaxy as it was 9 billion years ago, another, a quasar blazing from the universe's toddler years. Layer them together, and suddenly you're watching the universe grow up in fast forward, from a fog of primordial soup to the glittering web of galaxies we see today. And then there's the ultimate time capsule, the cosmic microwave background, the faint afterglow of the Big Bang itself. This ancient light, cooler than the deepest shadows of space, holds the blueprint for everything that followed. Patterns in its faint glow reveal the seeds of galaxy clusters and the echoes of quantum fluctuations from the universe's first trillionth of a second. Telescopes like the Planck satellite map these whispers in exquisite detail, turning them into a Rosetta Stone for cosmic history. So when you hear about a telescope capturing light from the early universe, remember, it's not just a snapshot. It's a message in a bottle sent across eons, carrying secrets about how stars ignite, how galaxies collide, and how the very fabric of reality stretches and twists. And with every new observation, we're adding another piece to the greatest puzzle of all, the story of us. The cosmic microwave background isn't just light, it's the universe's baby picture, frozen in time. Imagine rewinding the cosmos to just 380,000 years after the Big Bang, when the entire universe was a glowing fog of plasma, hot as the surface of the sun. Then, in a cosmic instant, everything changed. Atoms formed, the fog cleared, and light broke free for the first time. That flash, stretched and cooled by 14 billion years of expansion, is what we now detect as a faint microwave whisper, bathing every corner of space. What makes this glow so extraordinary are the tiny imperfections, ripples no warmer than a few millionths of a degree. These aren't random, they're the universe's first brushstrokes, the gravitational seeds from which galaxies would eventually grow. When satellites like Planck mapped these fluctuations in exquisite detail, they revealed something astonishing: the exact distribution of matter at the dawn of time, a blueprint for everything that followed. Dark matter, invisible and mysterious, left its fingerprints here too, tugging at the primordial plasma like unseen hands shaping clay. But the real magic lies in how this ancient light connects to us. Every microwave photon hitting a telescope today has traveled uninterrupted since the universe was 1,000 times smaller than a single grain of sand. It's a direct line to our cosmic origins, carrying echoes of quantum fluctuations so tiny they existed long before atoms or stars. And hidden within those echoes are answers to profound questions: why the universe is lumpy instead of smooth, how galaxies found their places, even what might have happened in the first trillionth of a second before this light was born. Now, as we turn our gaze to quasars, keep this in mind. They're not just distant beacons. These brilliant objects act like cosmic magnifying glasses, bending and amplifying the CMB's ancient light as it passes through them. It's as if the universe left us two ways to read its oldest message, one written in the faint glow of its birth, and another magnified by the most powerful engines in existence. Quasars are like cosmic lighthouses, blazing through the fog of time with such intensity that we can spot them from billions of light years away. But these aren't just any bright objects, they're the active hearts of distant galaxies, powered by supermassive black holes greedily devouring surrounding matter. As material spirals into these black holes, it heats up to unimaginable temperatures, creating jets and disks that outshine entire galaxies. This incredible brightness isn't just for show, it's a tool, cutting through the darkness of the early universe like a searchlight, illuminating everything in its path. When quasar light journeys across the cosmos, it doesn't travel untouched. It passes through vast clouds of gas, absorbing certain wavelengths and leaving behind telltale gaps in its spectrum. Astronomers study these gaps like detectives analyzing fingerprints, uncovering the composition of gas clouds that existed when the universe was young. Some of these clouds are so ancient they contain almost nothing but hydrogen and helium, the pristine building blocks of the cosmos before stars had a chance to forge heavier elements. Others show traces of carbon, oxygen, and iron, telling us exactly when and where the first generations of stars began seeding the universe with the ingredients for planets and life. But quasars do more than just reveal the chemistry of deep space. Their light bends and warps as it passes through the invisible scaffolding of dark matter, allowing scientists to map the cosmic web, the vast, interconnected structure of galaxies and voids that defines the universe's large-scale architecture. By studying distortions in quasar light, astronomers can trace where dark matter clumps and how it shapes the growth of galaxies over billions of years. It's like using a flashlight to cast shadows on an unseen sculpture, revealing its form through the patterns it creates. And here's where it gets even more fascinating. Some quasars are so distant that their light has been traveling for nearly the entire age of the universe. When we observe them, we're catching glimpses of black holes that existed when galaxies were just beginning to assemble, offering crucial clues about how these cosmic monsters grew so massive so quickly. Were they born big, or did they merge and feast in a frenzy? Quasar light holds the answers. Now, imagine those same beams of ancient light, after journeying across the cosmos, also carry faint echoes of the cosmic microwave background, the afterglow of the Big Bang. When quasar light passes through particularly dense regions of space, it interacts with this primordial radiation, creating subtle shifts that scientists can measure. It's as if the universe left us multiple ways to decode its history, one written in the glow of its birth and another amplified by the brightest objects in existence. So the next time you hear about a distant quasar, remember it's not just a faraway beacon. It's a time machine, a cosmic chemist, and a dark matter detective all rolled into one. And as we turn our gaze to the invisible hand shaping the universe, we'll see how starlight exposes the mysteries of dark matter, the ghostly force that binds galaxies together yet remains just out of sight. Dark matter might be invisible, but it leaves its mark everywhere, especially in the way it warps starlight like a cosmic funhouse mirror. This ghostly substance doesn't emit, reflect, or absorb light, yet its gravitational grip is so strong it bends the very fabric of space-time, distorting the paths of photons traveling billions of years to reach us. Astronomers call this effect gravitational lensing, and it's one of the most powerful tools we have for mapping the invisible skeleton of the universe. Picture a massive galaxy cluster floating in space. Its visible stars and gas are just the tip of the iceberg. The real weight comes from the dark matter halo enveloping it. When light from a more distant galaxy passes through this region, the dark matter's gravity acts like a lens, twisting and magnifying the light into arcs, rings, or even multiple copies of the same galaxy. It's as if the universe itself is holding up a magnifying glass, revealing secrets we could never see otherwise. By measuring these distortions, scientists can reconstruct the hidden mass, tracing dark matter's distribution with astonishing precision. What's truly staggering is the scale of dark matter's influence. Without it, galaxies would fly apart, their stars orbiting so fast that visible matter alone couldn't hold them together. Take our Milky Way. Its outer stars whip around at speeds that defy the laws of gravity as we know them, unless there's an invisible anchor weighing things down. That anchor is dark matter, a cosmic glue making up roughly 27% of the universe's total mass and energy. But dark matter isn't just holding galaxies together. It's also the architect of the universe's large-scale structure. In the early cosmos, tiny fluctuations in dark matter density acted like gravitational seeds, pulling ordinary matter into the filaments and nodes we now see as galaxy clusters and superclusters. Without this hidden scaffolding, the universe would look entirely different. No grand cosmic web, no glittering cities of galaxies. Yet for all its importance, dark matter remains maddeningly elusive. We know it's there because of the way it sculpts light, but we still don't know what it's made of. Is it a sea of exotic particles, a shadow universe with its own set of physical laws? Every twisted arc of lensed starlight brings us closer to answers, but the mystery endures. And as we'll soon discover, this interplay between light and shadow doesn't just shape galaxies. It also holds clues to the universe's accelerating expansion, a puzzle even more profound than dark matter itself. Edwin Hubble's telescope wasn't just a window to the stars, it was a mirror reflecting a universe in motion. One night in the 1920s, as he measured the faint glow of distant galaxies, he noticed something extraordinary. Their light wasn't just dim, it was stretched, shifted toward the red end of the spectrum like a cosmic sigh. This redshift meant the galaxies were racing away from us, and the farther they were, the faster they fled. It was as if the universe itself was breathing, expanding in every direction at once. That single observation shattered the idea of a static cosmos and set the stage for the most revolutionary theory of all, the Big Bang. But redshift isn't just a relic of the past, it's a living language, still whispering secrets about how space stretches and grows. Take supernova, the violent explosions of dying stars. These brilliant flashes are so consistent in their brightness that astronomers call them standard candles. By measuring how dim they appear versus how bright they should be, scientists can calculate their distance with remarkable precision. And here's where things get strange. When researchers compared distant supernovae to nearby ones in the late 1990s, they expected to see the universe's expansion slowing down, pulled by gravity's relentless tug. Instead, they found the opposite. The light from these ancient explosions revealed an unsettling truth. The cosmos isn't just expanding, it's accelerating, as if some invisible force is pushing galaxies apart faster and faster. That force is dark energy, a mystery even deeper than dark matter. Unlike its shadowy cousin, dark energy doesn't clump or pull. It permeates empty space itself, acting like anti-gravity on a cosmic scale. And ancient starlight is our best tool for understanding it. By studying the redshift of galaxies and supernova across billions of years, astronomers can trace how dark energy's influence has changed over time. The results are humbling. This energy makes up nearly 70% of the universe's total content, yet we still don't know what it is. Is it a property of space itself? A new kind of field, or something beyond our current physics? Every photon from the early universe carries clues, and the answers might rewrite our understanding of reality. Now let's rewind even further, to a time before galaxies, before dark energies reign, when the first stars flickered to life in a pitch-black cosmos. These pioneers weren't like the stars we see today. Born from pure hydrogen and helium, they burned hot and fast, forging the first heavy elements in their cores before exploding in spectacular supernovae. Their light, long since faded, left an indelible mark on the universe. It ionized the fog of primordial gas, clearing the way for galaxies to form. It seeded space with carbon, oxygen, and iron, the building blocks of planets and life. And most remarkably, we can still detect echoes of their existence in the faint glow of distant quasars, their light stained by the fingerprints of those first stellar giants. This is the power of ancient starlight. It's not just a record of where we've been, it's a compass pointing to where we're going. Will dark energy tear the universe apart? Or will it fade, leaving gravity to pull everything back together in a cosmic reversal? The answers are written in the light of stars long dead, waiting for us to decipher their message. And as we peer deeper into the past, we're not just uncovering the history of the cosmos, we're reading our own origin story, one photon at a time. Imagine a universe without stars, no twinkling lights, no galaxies, just an endless sea of darkness. That was our cosmos in its infancy, a place where hydrogen gas floated like an invisible fog, blocking light from traveling freely. Then, around 100 million years after the Big Bang, something extraordinary happened. Gravity began pulling clumps of this gas together, squeezing them tighter and tighter until the pressure ignited nuclear fusion. And just like that, the first stars were born. These weren't like the stars we see today. They were titanic, hundreds of times more massive than our sun, and they blazed with an intensity we can barely fathom. Their ultraviolet radiation was so powerful it ripped electrons from hydrogen atoms, turning the universe's opaque fog into a transparent ocean of ionized gas. Astronomers call this transformation Re-ionization, and it marked the end of the cosmic dark ages. But how do we know this happened? The proof is written in the light of quasars. When their beams travel through these ancient ionized regions, their spectra carry telltale gaps, absorption lines that act like a cosmic barcode, revealing when and where the fog lifted. Yet these first stars did more than just light up the cosmos. Inside their cores, they forged elements heavier than hydrogen and helium, carbon, oxygen, even traces of iron. Then, in spectacular supernova explosions, they scattered these elements into space like cosmic gardeners planting seeds for future generations. Without those explosions, there would be no planets, no life, no us. But here's the twist: we'll never see these stars directly. Their light has been stretched by the expanding universe into infrared wavelengths, far beyond what our eyes can detect. Instead, we find their fingerprints everywhere in the chemistry of ancient gas clouds, in the oldest stars of our galaxy, even in the elements that make up our own bodies. What's truly astonishing is how quickly these pioneers changed everything. In cosmic terms, they lived fast and died young, their brilliant lives lasting only a few million years. But their legacy echoes across time. The heavy elements they created became the building blocks for everything that followed: new stars, planets, and eventually life itself. And when we look at the night sky today, we're not just seeing points of light. We're witnessing the aftermath of a revolution that began billions of years ago, when the first stars dared to shine in the darkness. Now, let's follow those elements on their next great journey scattered by supernova. They would become the raw material for an even richer universe, one where stars could form with planets, and planets could give rise to life. Some stars don't fade quietly, they go out with a bang so powerful it can outshine entire galaxies. These supernova are nature's ultimate alchemists, transforming simple elements into the building blocks of life itself. When a massive star exhausts its nuclear fuel, gravity wins in seconds, collapsing its core with such force that it rebounds in a shockwave of unimaginable energy. In that explosive instant, temperatures soar beyond 1 billion degrees, forging heavy elements like gold, uranium, and iron materials that would never form under ordinary stellar conditions. Then, like cosmic shrapnel, these elements blast outward at nearly 10% the speed of light, seeding interstellar space with the raw ingredients for planets and life. We see their fingerprints everywhere. Take our own solar system, the iron in your blood, the calcium in your bones, even the silicon in your phone's microchips all originated in ancient stellar explosions. Astronomers find these elemental signatures etched into the spectra of second-generation stars, acting like time capsules from the universe's early chemical factories. By comparing the ratios of elements in old stars, scientists can reconstruct entire family trees of supernova, revealing which ones lived fast and died young versus those that simmered for billions of years before exploding. But supernova don't just create, they also destroy and renew. Their shockwaves plow through interstellar gas like cosmic snowplows, compressing clouds so dense that new stars ignite within them. The Orion Nebula, that glowing stellar nursery visible to the naked eye, was likely jump-started by a supernova's violent push. It's a stellar circle of life, death giving birth to new possibilities across the galaxy. Perhaps their most surprising role is as cosmic measuring sticks. Type Ia supernova, which occur when white dwarf stars steal too much mass from companions, all explode with remarkably consistent brightness. This makes them perfect standard candles for measuring mind-bending distances. When astronomers discovered these explosions appeared dimmer than expected in distant galaxies, it led to the Nobel Prize-winning revelation that the universe's expansion is accelerating, propelled by the mysterious force we call dark energy. Now picture this, some of the light reaching Earth tonight comes from supernova that detonated before our planet even formed. These photons have traveled for millions of years, carrying stories of stellar demise that shaped the chemistry of our world. And when we trace their paths backward, we begin to see how these explosions didn't just fill space with elements, they orchestrated the grand construction project of galaxies themselves. Galaxies don't just appear fully formed, they're built over billions of years, piece by piece, in a cosmic construction project written in Starlight. Take GNZ 11, one of the most distant galaxies ever observed. Its light has traveled for over 13 billion years to reach us, showing a universe in its messy infancy. This galaxy is nothing like the elegant spirals we see today. It's small, chaotic, and blazing with newborn stars, a far cry from the orderly structures we recognize. But hidden in its glow are the blueprints for everything that followed. How does a galaxy grow up? It starts with mergers, violent, slow-motion collisions where smaller galaxies smash together, their gravity tangling like cosmic spaghetti. Each merger sends shockwaves through clouds of gas, triggering bursts of star formation and reshaping entire structures. You can still see evidence of this today in galaxies like the Milky Way, where streams of stars, relics of ancient mergers, arc across the night sky like celestial brushstrokes. But mergers aren't the only architects. Supermassive black holes lurking at the hearts of galaxies play a surprising role too. When these monsters feast on surrounding gas, they unleash torrents of energy that can heat up or even blow away a galaxy's star-forming fuel. It's a cosmic balancing act. Too much black hole activity stifles growth, while too little lets gas run wild, creating stars uncontrollably. Starlight carries the echoes of this dance, with some galaxies showing scars from past black hole outbursts, while others reveal the quiet persistence of steady growth. And then there's the gas, the invisible scaffolding of galaxy formation. Most of it isn't the stuff of stars yet, just cold, dark hydrogen waiting to collapse. When astronomers study the spectra of distant galaxies, they can spot this gas by the way it absorbs specific wavelengths of starlight, like a cosmic barcode revealing the raw materials still up for grabs. Some galaxies are voracious, sucking in gas from intergalactic space to fuel new generations of stars. Others, like our own Milky Way, are more restrained, forming stars at a leisurely pace. Yet the story isn't over. Even now, galaxies continue to evolve. The Andromeda Galaxy, our nearest neighbor, is on a collision course with the Milky Way, a merger that will reshape both in about 4 billion years. By then, the starlight we see today will have become part of a new chapter, one future astronomers might decode just as we're doing now. But there's a puzzle hidden in all this light. Where is the rest of the universe's ordinary matter? Stars and gas account for only a fraction of what should exist. The answer lies in the faint glow between galaxies, in threads of superheated plasma woven through the cosmic web. And the key to finding it, once again, ancient starlight, carrying clues about the universe's missing pieces. The universe has a missing matter problem, not dark matter this time, but the ordinary stuff that makes up stars, planets, and even us. If you tally all the protons and neutrons that should exist based on the Big Bang's chemistry, nearly half of them are unaccounted for. It's like doing a cosmic inventory and finding an entire warehouse of materials vanished without a trace. But here's the twist: that matter isn't gone. It's hiding in plain sight, woven into the fabric of the universe itself, and ancient starlight is how we're finally tracking it down. This missing matter, what scientists call the missing baryon problem, and isn't lost in black holes or locked inside invisible planets. Instead, it's floating in vast, diffuse filaments of superheated gas, stretching between galaxies like the threads of a spider's web. These filaments are part of the cosmic web, the large-scale structure of the universe, where galaxies cluster at the intersections like glittering beads on invisible strings. The gas is so hot, millions of degrees, that it doesn't form stars or emit much light. But when the brilliant beam of a quasar passes through it, the gas leaves its mark, absorbing specific wavelengths of ultraviolet light like a cosmic barcode. Astronomers call these absorption lines the Lyman alpha forest, a whimsical name for a phenomenon that's anything but simple. Each dip in the quasar's spectrum represents a clump of gas at a different distance, allowing scientists to map the distribution of this elusive matter in 3 dimensions. It's as if the universe dipped its fingers in ink and pressed them across the light, leaving fingerprints of its hidden structure. And when researchers pieced these maps together, they found something astonishing. The missing baryons aren't missing at all. They're just too hot and spread out to see directly, like steam rising from a boiling pot, invisible until you know where to look. Solving this mystery isn't just about balancing the cosmic books. These filaments are the universe's circulatory system, channeling gas into galaxies and fueling the birth of new stars. Without them, galaxies would starve, their growth stunted by a lack of raw materials. But there's a deeper story here. The way this gas is distributed, its temperature, its density holds clues to how the cosmic web formed in the first place, shaped by the gravitational tug of dark matter and the explosive energy of supernova. Now, imagine rewinding even further to a time before this web took shape, when the first molecules in the universe began to form. These weren't the complex compounds we know today, just simple pairings like hydrogen and helium hydride, the universe's first chemical handshake. Their faint signals, etched into starlight, mark the moment the cosmos grew cool enough for chemistry to begin, setting the stage for everything that followed. The universe wasn't always a chemist. For the first 100,000 years after the Big Bang, it was too hot for atoms to even hold hands, just a swirling plasma of solitary protons, electrons, and helium nuclei racing through space at unimaginable speeds. Then, as the cosmos cooled, something extraordinary happened. A helium nucleus captured a single electron, forming the universe's first molecule, helium hydride. This fragile pairing was more than just a scientific curiosity. It was the spark that ignited cosmic chemistry, setting in motion the chain of events that would eventually lead to planets, oceans, and life itself. Detecting these pioneer molecules isn't easy. Their infrared signatures are faint, stretched by billions of years of cosmic expansion into whispers barely distinguishable from background noise. That's where telescopes like SOFIA, a modified Boeing 747 carrying a massive infrared observatory, come in. Flying above most of Earth's water vapor, SOFIA instruments caught the fingerprint of helium hydride in a distant nebula, confirming predictions made decades earlier. It was like finding the first brushstroke on a canvas that would eventually become the Mona Lisa. But helium hydride was just the opening act. Soon after, hydrogen molecules formed, two hydrogen atoms bound together in the simplest possible union. These unassuming pairs became the universe's first refrigerants, allowing gas clouds to shed heat and collapse into the dense knots that ignited the first stars. Without them, the cosmos might have remained a featureless void, too hot to birth the stellar furnaces that forged heavier elements. What's astonishing is how these molecular handshakes echo across time. The same infrared signals we detect in distant nebulae today mirror processes that unfolded when the universe was less than 1% of its current age. By studying them, we're essentially watching chemistry's Big Bang moment. The instant simple particles began cooperating to build something greater than themselves. And then there's the ultimate twist. These humble molecules laid the groundwork for life. The carbon in your DNA, the oxygen in your lungs, even the iron in your blood. All were forged in stars that couldn't have existed without those first cooling clouds of molecular hydrogen. Every breath you take connects you to that ancient chemical dawn, a legacy written in starlight and waiting to be decoded. Now, as we turn from chemistry to time itself, remember this: the light carrying these stories doesn't just show us the past, it bends and twists with the fabric of space, revealing how the universe stretches and grows. The same photons that witnessed the first molecules also carry imprints of cosmic expansion, a ticking clock woven into the very waves that bring their message to us. Every time you gaze at the Andromeda Galaxy, you're not just seeing light, you're stepping into a time machine. That soft glow stretching 2.5 million light-years means you're witnessing Andromeda as it looked when early humans were first walking the Earth, long before pyramids or cities existed. This same principle transforms every telescope into a window to the past. The farther we peer into space, the deeper we dive into cosmic history. The light from your backyard stars might be decades or centuries old, but venture further, and you'll find galaxies frozen in their adolescence, their light only now reaching us after traveling for billions of years. Take Max 1149, one of the most distant galaxies ever observed. Its light began journeying toward us when the universe was just 500 million years old, a mere toddler by cosmic standards. When astronomers capture this ancient glow, they're not just measuring distance. They're watching galaxies take their first steps, seeing how they grew from chaotic, misshapen blobs into the majestic spirals and ellipticals we recognize today. Each photon is a snapshot of a specific cosmic era, allowing us to assemble a flipbook of universal evolution. But the real magic happens when we combine these observations. By comparing galaxies at different distances, and therefore different ages, we can watch universal changes play out in real time. Nearby galaxies show mature, settled structures, while their more distant counterparts reveal violent bursts of star formation, frequent collisions, and supermassive black holes running wild. It's like having a photo album where each page shows the universe at a different stage of life, from infancy to adulthood. Neutron stars take this time-traveling light to even greater extremes. These ultra-dense stellar corpses, so compact that a teaspoon of their material would weigh 1 billion tons, spin hundreds of times per second, sending out beams of radiation like cosmic lighthouses. When these beams sweep past Earth, we detect them as precise pulses, some ticking with more accuracy than atomic clocks. But here's what makes them extraordinary time capsules. The light from these pulsars carries imprints of their mind-bending physics, gravity so strong it warps space-time, magnetic fields powerful enough to shred atoms, and densities that defy earthly logic. By studying how this light behaves as it escapes such extreme environments, we're essentially running experiments in conditions impossible to recreate on Earth. Some neutron stars have been pulsing steadily for millennia, their rhythmic flashes crossing interstellar space like the universe's own metronome. Others, locked in deadly dances with companion stars, reveal how matter behaves when ripped apart by tidal forces and compressed into event horizons. Each pulse is a message in a bottle, carrying data about the laws of physics pushed to their breaking point. And just like ancient starlight, these signals take years, centuries, or millennia to reach us, making every observation a glimpse into the star's past state. What's truly humbling is realizing how much history is still traveling toward us unseen. Right now, light from galaxies being born, stars exploding, and planets forming is racing through the void photons that will only reach Earth long after we're gone. The cosmos doesn't just keep secrets in space, it hides them in plain sight, encoded in light that hasn't arrived yet. And with every technological leap, from radio telescopes to gravitational wave detectors, we're building better machines to decode these messages from the past and perhaps catch whispers of futures yet to come. Neutron stars are nature's ultimate physics experiments, cosmic pressure cookers where matter gets squeezed beyond imagination. Picture a star so dense that its atoms collapse into a sea of neutrons, packing the mass of our sun into a sphere smaller than Manhattan. The gravity on their surface is 100 billion times stronger than Earth's, bending light so severely that if you could stand on one, which you couldn't, you'd see the back of your own head from the way photons curve around the star. This extreme environment turns neutron stars into perfect laboratories. Take pulsars, the lighthouses of the cosmos. These rapidly spinning neutron stars emit beams of radio waves so precise they rival atomic clocks. When the first pulsar was discovered in 1967, its rhythmic pulses were so regular that astronomers jokingly labeled it LGM1, short for Little Green Men. But the truth was even stranger. A stellar corpse spinning faster than a kitchen blender, its magnetic field a quadrillion times stronger than Earth's, whipping particles to near light speed. Then there are Magnifiers, neutron stars with magnetic fields so intense they could wipe a credit card clean from halfway across the solar system. Occasionally, these stars suffer starquakes, sudden crust fractures that release gamma-ray flares visible across the universe. In 2004, a Magnifier 50,000 light-years away unleashed a burst so powerful it briefly ionized Earth's upper atmosphere, even though the star itself would be invisible to the naked eye. But neutron stars truly shine literally when they collide. When two of these ultra-dense objects spiral into each other, they create fireworks visible across the electromagnetic spectrum. The 2017 detection of a neutron star merger by LIGO gravitational wave observatories marked a new era. For the first time, astronomers saw ripples in space-time alongside a brilliant glow of light. The aftermath was even more astonishing. Over days, the collision's debris faded from blue to red as it produced staggering amounts of heavy elements, enough gold to outweigh Earth several times over. Every platinum ring or uranium fuel rod on our planet likely began in such a cataclysmic event. What makes these observations revolutionary is how they bridge cosmic scales. The gravitational waves from merging neutron stars travel at light speed, arriving milliseconds before the gamma-ray burst, confirming Einstein's prediction that both move identically through space-time. Meanwhile, the light spectrum reveals freshly forged elements, proving that the universe's heaviest atoms aren't made in supernova alone. These collisions are cosmic alchemy in action, transforming simple matter into the building blocks of planets and life. Yet neutron stars still guard secrets. Some pulse erratically, as if something inside is rearranging their cores. Others mysteriously accelerate their spins, hinting at quantum phenomena we've yet to understand. And a few, when observed through X-ray telescopes, show surface hotspots hotter than physics should allow possibly evidence of exotic states of matter where neutrons dissolve into quark soup. As we turn toward black holes, remember this: neutron stars are the last stop before matter vanishes forever. Their light, whether as precise pulsar ticks or merger afterglows, gives us front-row seats to physics at its most extreme. And when that light finally reaches us after centuries or millennia of travel, it carries more than data. It brings stories of stellar demise, quantum rebellion, and the violent births of elements we hold in our hands every day. Black holes may be the ultimate cosmic paradox, regions where gravity is so strong that not even light can escape, yet they create some of the brightest spectacles in the universe. Picture a swirling maelstrom of superheated gas, spiraling toward the event horizon at nearly the speed of light. Friction heats this accretion disk to millions of degrees, causing it to glow fiercely in X-rays, a beacon visible across cosmic distances. It's like watching water circle a drain, but in this case, the drain is a gravitational monster, and the water is a searing inferno broadcasting its presence to the cosmos. These X-ray whispers aren't just pretty, they're packed with information. By analyzing the flickering patterns of light from accretion disks, astronomers can measure a black hole's spin, a property as fundamental as its mass. A rapidly spinning black hole drags space-time around it like a whirlpool, warping the inner edge of the disk closer to the event horizon. The resulting X-ray fluctuations act like a cosmic strobe light, revealing whether the black hole is lazily twirling or spinning fast enough to twist the fabric of reality itself. But the real fireworks happen when black holes launch jets, twin beams of particles accelerated to nearly the speed of light. These jets, often stretching thousands of light years, shine across the entire electromagnetic spectrum, from radio waves to gamma rays. Their origins are still mysterious, but magnetic fields near the black hole's poles likely act like cosmic railguns, slinging charged particles outward with unimaginable force. Some jets, like those from the galaxy M87, are so powerful they've been imaged directly, their eerie glow-tracing paths through intergalactic space. Even black holes that go on a cosmic diet, starving their accretion disks, can't hide completely. Their gravity bends and magnifies light from stars behind them, a phenomenon called gravitational lensing. In 2019, astronomers witnessed a star's light stretch and brighten as it passed behind a dormant black hole, its image warped into a perfect Einstein ring. This ghostly halo confirmed the black hole's presence as clearly as any X-ray flare, proving darkness can still cast a shadow. Now, imagine trying to read these cosmic messages while someone keeps turning up the lights. Just as city glare drowns out stars, human-made radio interference and satellite megaconstellations are muddying the skies. The same X-rays and radio waves that reveal black holes must now compete with our electronic noise, threatening to obscure the universe's oldest language. Yet, even as we pollute the cosmic signals, we're building tools to listen more carefully than ever, because the story of black holes isn't just about darkness. It's about the light they force into being, the way they twist physics into fireworks, and the urgent race to decode their brilliance before it fades into humanity's static. Imagine trying to listen to a whisper in a roaring stadium. That's what astronomers face when they peer through the glow of city lights to study the cosmos. Light pollution doesn't just dim the stars, it erases them, washing out all but the brightest celestial objects. The Milky Way, once a shimmering river visible to every human civilization, now hides from 1/3 of humanity, veiled behind an orange haze of streetlights and neon signs. For researchers, this isn't just an aesthetic loss, it's a scientific crisis. The faint glow of distant galaxies, the delicate filaments of the cosmic web, even the subtle echoes of the Big Bang itself are drowned out by our artificial skies. Take the Sloan Digital Sky Survey, one of history's most ambitious galaxy mapping projects. Its telescopes in New Mexico must now compete with Albuquerque's expanding glow, forcing astronomers to abandon certain wavelengths of light entirely. Similarly, the Vera Rubin Observatory in Chile, designed to detect asteroids and dark matter, faces a growing threat from coastal cities encroaching light. The problem is so severe that some observatories have resorted to light curfews, negotiating with local governments to dim or shield fixtures during critical observations. Yet there are places where the night still speaks clearly. The Atacama Desert in Chile, high atop the Andes, hosts some of the world's last pristine skies. Here, under air so dry it steals moisture from your breath, telescopes like ALMA and the upcoming extremely large telescope capture starlight untouched by human interference. These dark sky preserves are more than scientific sanctuaries, they're time machines, offering glimpses of the universe as it appeared before the electric age. The fight against light pollution isn't just about astronomy. Misdirected artificial light disrupts ecosystems, confusing sea turtle hatchlings, disorienting migratory birds, and altering predator-prey dynamics. It even affects human health, with studies linking excessive nighttime light exposure to sleep disorders and increased cancer risks. Simple solutions like shielded fixtures that direct light downward or warmer-colored LEDs can slash energy waste by up to 60% while restoring the stars. What's truly at stake is more profound than data or energy savings. For millennia, humans navigated by the stars, told time by their movements, and wove them into myths and religions. That connection, the sense of wonder that comes from standing under a sky ablaze with distant suns, is slipping away. Every child who grows up never seeing the Milky Way loses a birthright older than civilization itself. Now imagine turning the tide, not just with professional observatories, but through armies of backyard astronomers. Armed with modest telescopes and smartphones, these citizen scientists are mapping light pollution, tracking vanishing stars, and even discovering distant supernovae. Their contributions prove that decoding the universe's whispers isn't just for those with billion-dollar telescopes. It's a conversation we can all join. You don't need a PhD to decode the universe, just curiosity and an internet connection. Projects like Galaxy Zoo have revolutionized astronomy by inviting ordinary people to classify galaxies from telescope images. Over 150,000 volunteers have helped sort through millions of cosmic snapshots, discovering rare galaxy mergers and peculiar structures professionals might have missed. It's like a celestial treasure hunt where anyone might stumble upon the next big breakthrough. Take the case of Hanny's voorwerpen, a strange green blob spotted by Dutch schoolteacher Hanny van Arkel while classifying galaxies. What began as an amateur observation turned into a scientific sensation, an immense cloud of gas glowing from the light of a long-dead quasar. This discovery, made possible by curious eyes outside academia, now helps astronomers understand how black holes shape their surroundings long after they've gone dark. But galaxy classification is just the beginning. Backyard astronomers with modest telescopes regularly track variable stars' celestial lighthouses that brighten and dim in predictable patterns. By measuring these changes, amateurs contribute data that helps calculate cosmic distances and uncover hidden companion stars. Some have even spotted supernovae before professional surveys, triggering alerts that bring the world's largest telescopes swiveling toward these stellar explosions. The real game changer, affordable spectroscopes that attach to amateur telescopes, letting enthusiasts dissect starlight just like the pros. When a hobbyist in Arizona analyzes the spectrum of a distant quasar or a retired teacher in Australia records the chemical fingerprints of a nebula, they're not just stargazing, they're expanding humanity's cosmic dataset. These observations help fill gaps between professional telescope time, creating continuous monitoring that's impossible for any single observatory. What makes this collaboration extraordinary is how it mirrors the light we study, countless individual contributions merging into something far greater. Every classified galaxy, every measured variable star, becomes part of a shared legacy, proving that the universe's story belongs to everyone. And as we stand on the brink of a new observational era, this partnership between professionals and passionate amateurs will only grow more vital. Soon, telescopes like the Vera Rubin Observatory will flood scientists with more data than any team could process alone. Its decade-long survey will capture changes across the entire southern sky every few nights, requiring an army of volunteers to spot cosmic oddities in the deluge. Meanwhile, space-based missions like Euclid and the Nancy Grace Roman Telescope will map millions of galaxies in unprecedented detail, each one a puzzle piece waiting for human eyes to place it. The future of cosmic exploration isn't just about bigger mirrors or sharper sensors, it's about connecting more people to the ancient light that's traveled so far to reach us. Whether you're clicking through galaxy images on a lunch break or pointing a backyard telescope toward Andromeda, you're joining a tradition that stretches back to the first humans who looked up and wondered. The stars have always been speaking. Now, more than ever, we're all learning how to listen. The next generation of telescopes won't just observe the universe, they'll rewrite its history books. Take NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. With a field of view 100 times wider than Hubble's, it will map millions of galaxies in infrared light, peering through cosmic dust to spot stellar nurseries invisible to current instruments. But its real power lies in something called gravitational microlensing, watching how distant stars briefly brighten when unseen planets or dark matter pass in front of them. This technique could reveal thousands of rogue planets drifting between stars and map dark matter's distribution with pixel-perfect precision. Meanwhile, on a mountaintop in Chile, the extremely large telescope is rising from the desert. Its 39-meter mirror, assembled from nearly 800 hexagonal segments, will collect more light than all of history's major telescopes combined. This behemoth won't just take pretty pictures. Its spectrographs will analyze the atmospheres of exoplanets for biosignatures like oxygen and methane. Imagine pointing this telescope at Proxima Centauri b and detecting chemical imbalances that could only exist if life were reshaping that world's air. But the most revolutionary might be the James Webb Space Telescope's successors, concepts like LUVOIR, a 12-meter space observatory that could directly image Earth-like worlds. Its coronagraph would block out starlight with such precision that nearby exoplanets would appear as pale blue dots, their atmospheres laid bare for analysis. Some designs even include star-shaped gigantic space flowers that would fly 40,000 kilometers ahead of telescopes to cast artificial eclipses, revealing planets normally lost in their star's glare. These instruments will push our vision closer to the cosmic dawn than ever before. The extremely large telescope's infrared eyes might catch population 3 stars, the universe's very first stellar generation, made purely of hydrogen and helium. These pioneers have never been seen directly. They lived fast, died young, and their light is so stretched by cosmic expansion that only next-gen telescopes can hope to spot their faint afterglow. Finding them would be like uncovering the fossilized footprints of the universe's first steps. What's truly staggering is the timescale these telescopes will explore. While Hubble showed us galaxies as they were 13 billion years ago, future instruments could push within a few 100 million years of the Big Bang, capturing the moment when the first stars ended the cosmic dark ages. Their light will carry fingerprints from an era when space was still filling with the first heavy elements, when the cosmic web was just beginning to form its glittering threads. And then there's the dark universe. By measuring how light bends around galaxy clusters with nanometer precision, these telescopes will trace dark matter's hidden architecture in 3 dimensions. Some might even catch evidence of dark matter particles annihilating in space, a faint glow that could finally reveal what this mysterious substance actually is. The most profound discovery might come from something as simple as a spectrum. When starlight passes through an exoplanet's atmosphere, certain molecules leave telltale absorption lines, like a barcode revealing that world's chemistry. Future telescopes could scan hundreds of these worlds, hunting for combinations of gases that don't appear together naturally. On Earth, oxygen and methane coexist only because life constantly replenishes them. Spotting that same unstable mixture elsewhere would strongly suggest we're not alone. These telescopes aren't just tools, they're time machines, built to answer questions we haven't even thought to ask yet. Every time humanity has built a better window to the cosmos, from Galileo's spyglass to Hubble, we've discovered that reality is stranger than our boldest theories. As these new observatories come online, they won't just show us deeper into space, they'll take us further back in time, to moments when the universe was inventing the rules as it went along. And somewhere in that ancient light, we might finally find our place in the story. Every atom in your body has a cosmic resume, a story that begins in the hearts of stars and stretches across billions of years. That calcium in your bones, forged in a supernova's violent death throes, the iron in your blood, smelted in a massive star's core before being scattered into space by stellar winds. Even the carbon that forms the backbone of your DNA was once stardust, drifting through interstellar clouds until gravity pulled it into the raw materials of our solar system. When you look up at the night sky, you're not just observing distant objects, you're meeting your ancestors. This connection runs deeper than chemistry. The same photons that carry ancient starlight to our telescopes also illuminate Earth, warming our planet and powering the photosynthesis that sustains life. Sunlight is literally starlight, a nearby example of the same cosmic process we study in distant galaxies. Every rainbow, every sunbeam is a local sample of the universe's grand light show, a reminder that we're embedded in the very phenomena we observe. What's truly humbling is the timeline. Consider that the light from the Andromeda galaxy left its source when early hominids were just learning to walk upright. The photons hitting your retina from the Orion Nebula began their journey as the pyramids were being built and the most distant galaxies we observe. Their light has traveled so long that Earth didn't exist when it started. We're seeing snapshots from before our planet, our sun. Even our Milky Way took their current forms. This perspective transforms how we see our place in the cosmos. The universe isn't just something out there, it's within us, around us, and through us. Those childhood moments of wonder beneath a starry sky weren't just imagination. They were the first stirrings of a deep biological recognition. We are the universe becoming aware of itself, tracing its own history through the light it created. Yet misconceptions abound. Some believe starlight shows the universe as it is now, not realizing we're always looking into the past. Others think telescopes act like time machines, physically transporting us backward rather than simply capturing old photons. And a persistent myth suggests dark matter is visible, that if we just build better telescopes, we'll see it directly. The truth is far more fascinating. Dark matter reveals itself not by shining, but by how it sculpts the light passing through it, like a silent potter shaping clay. The beauty of studying ancient light isn't just in unraveling cosmic mysteries, it's in how those revelations change us. When we learn that gold comes from neutron-star collisions, or that the water in our glasses once floated in interstellar space, the universe stops being abstract. It becomes personal. Every scientific paper about quasar spectra, every telescope image of a distant galaxy, is another page in humanity's collective origin story. And just as knowing family history can shape identity, understanding our cosmic lineage fosters something vital, a sense of belonging to a story far grander than ourselves. Now let's untangle some common mix-ups. When astronomers say they're looking back in time, they don't mean breaking physics. They're simply acknowledging light's finite speed. The misconception that we could ever see the universe as it is now ignores a fundamental truth. Now is a local concept across cosmic distances. Now loses meaning. A civilization in Andromeda observing Earth today would see dinosaurs, not skyscrapers, not because they've traveled back in time, but because that's when their incoming light left here. This relativity of now isn't science fiction. It's how light carries history to us, one delayed photon at a time. Another myth worth dispelling, that space is mostly empty. Between galaxies, yes, but within them, the interstellar medium teems with complex molecules. From simple water ice clinging to dust grains to organic compounds like ethanol floating in nebulas, space is more like a faint, sprawling chemical soup than a perfect vacuum. Even the empty patches distort starlight subtly, leaving fingerprints that reveal their hidden contents. Perhaps the most poetic misconception is that starlight fades with distance because it gets tired. In reality, light loses energy not from exhaustion, but because the universe stretches it like a cosmic slinky being pulled apart. This redshift preserves every photon's information, just in a lower energy state. Far from being a limitation, this stretching is why we can read the universe's history at all without it. The earliest light would be too energetic to detect safely. As we peel back these layers of misunderstanding, something remarkable happens. The universe stops being a collection of pretty pictures and becomes a dynamic, interconnected system, one we're part of, not just observers of. And with that shift comes a responsibility to preserve our ability to keep reading these ancient messages. whether by protecting dark skies or supporting the next generation of cosmic storytellers. Because the light hasn't stopped coming, and neither should our curiosity, Starlight holds incredible secrets, but it's not the cosmic oracle some imagine. Unlike sci-fi tropes where beams of light carry encrypted alien greetings or prophetic visions, real starlight is far more subtle and far more fascinating. Those twinkling points in the night sky aren't broadcasting messages from distant civilizations. They're silent witnesses to the universe's past, carrying data about chemical compositions, temperatures, and motions, not deliberate communication. The idea of decoding an alien radio signal from starlight might make for gripping fiction, but the truth is, if extraterrestrials wanted to chat, they'd likely use more direct methods like targeted radio waves or laser pulses rather than relying on the scattergun approach of starlight. Another common misconception that telescopes show us the universe as it is right now. In reality, every glance at the stars is a peek into history. The light from Proxima Centauri, our nearest stellar neighbor, takes over 4 years to reach us, meaning we're seeing it as it was when that light began its journey, not as it exists today. For galaxies millions or billions of light years away, we're effectively looking at cosmic snapshots from an era when Earth was barren or didn't even exist. This delay isn't a flaw, it's a feature, giving us a layered timeline of the universe's evolution. Then there's dark matter, the universe's most pervasive ghost. Starlight can't illuminate it directly because dark matter doesn't interact with light at all. No absorption, no reflection, no emission. Instead, its presence is inferred through gravity's grip on the visible universe. When light bends around a galaxy cluster in a gravitational lens, it's not because of the stars we see, it's the unseen mass of dark matter warping space-time, like an invisible hand pressing on a rubber sheet. And what about the edges of reality? Starlight has a hard limit, the observable universe. Beyond a certain point, the expansion of space stretches light so much that it fades into undetectability, like a ship disappearing over the horizon. No telescope, no matter how powerful, can see beyond this cosmic curtain, not because the universe ends there, but because the light from farther regions hasn't had time to reach us in the universe's 13.8 billion-year lifespan. These limitations aren't shortcomings, they're boundaries that define what makes starlight so extraordinary. It doesn't need to predict the future or reveal hidden dimensions to be awe-inspiring. Its real power lies in its honesty, delivering unaltered records of cosmic events without artifice or agenda. Every photon is a faithful messenger, traveling billions of years just to whisper, "This is how things were." Now consider how differently cultures have heard those whispers. For some, stars were ancestral spirits. For others, celestial maps or omens. These interpretations weren't primitive guesses, they were humanity's first attempts to translate a language we're still learning to read today. The myths may have faded, but the wonder remains, bridging ancient stargazers and modern scientists in a shared quest to understand the lights above. Long before telescopes or spectrographs, humanity's relationship with starlight was written in stories and stone. The ancient Egyptians aligned their pyramids with Orion's belt, believing the pharaoh's soul would travel that celestial pathway to the afterlife. Polynesian navigators memorized star compasses so precise they could sail thousands of miles across open ocean by reading the night sky like a map. For the Inca, the dark patches of the Milky Way weren't empty space. They were celestial animals, with the emu in the sky guiding seasonal harvests across generations. These weren't primitive myths, they were sophisticated cosmic languages, encoding survival knowledge in memorable narratives. Take the Aboriginal songlines of Australia, interwoven stories mapping landscapes through stars that served as both navigation charts and legal documents. The Seven Sisters constellation doesn't just mark seasons, it tells an epic chase story across the sky, warning of seasonal changes while preserving cultural memory. Similarly, the Babylonians didn't just track Venus for agriculture. They saw it as the goddess Ishtar moving between underworld and heaven, blending astronomy with theology in clay tablets that became the first known star catalogues. What's remarkable is how these traditions often anticipated modern science. The Maori story of Ranginui and Papatuanukus, Sky Father and Earth Mother forced apart by their children, eerily mirrors the Big Bang's separation of cosmic background radiation from matter. Norse mythology described a primordial void called Ginnungagap where fire and ice collided to form worlds, not unlike modern theories of cosmic inflation. While these cultures lacked our instruments, their observations were startlingly accurate. The Dogon people of Mali knew Sirius had an invisible companion star centuries before telescopes confirmed Sirius B, and Mayan astronomers calculated Venus cycles with precision rivaling modern ephemerides. These celestial stories did more than explain the cosmos. They shaped human civilization. Stonehenge's heel stone marks the summer solstice sunrise, aligning a calendar in stone. The Nebra sky disk, buried in Germany 4,000 years ago, shows the oldest known representation of cosmic phenomena, with gold arcs tracing the sun's path between solstices. Even today, we unconsciously echo these traditions. Our weekdays named for celestial bodies, Sun Day, Moon Day, Tuesday for Mars, carry the legacy of astrological systems older than Rome. The shift from mythological to scientific understanding wasn't a rejection of wonder but an expansion of it. When Galileo turned his telescope to the Milky Way and saw it resolved into countless stars, he didn't dismiss Dante's vision of it as a heavenly road. He added new layers to its mystery. Modern astrophysics continues this tradition, using starlight to uncover cosmic history much as ancestors used it to mark time. The difference lies not in curiosity but in methodology, swapping oral traditions for spectrometers while pursuing the same eternal questions. Nowhere is this continuity more vivid than in art. Vincent van Gogh's Starry Night swirls with the same awe that inspired Navajo star ceilings, while contemporary installations like The Morning Line use astrophysical data to generate celestial soundscapes. From Gustav Holst's The Planets to Björk's Cosmogony, musicians have translated cosmic rhythms into harmonies, proving starlight still stirs creativity, just as it once guided voyages and shaped myths. The universe's oldest language hasn't stopped speaking, we've simply learned new ways to listen. Vincent van Gogh didn't just paint the night sky, he captured its electric heartbeat. In Starry Night, those swirling, luminous vortices weren't mere imagination. They were the artist's attempt to translate cosmic turbulence onto canvas, long before science confirmed the dynamic chaos of galaxies. His brushstrokes mirror the very molecular clouds where stars are born, proving art often anticipates scientific insight. But Van Gogh wasn't alone in this celestial conversation. Centuries earlier, Hokusai's woodblock prints framed Mount Fuji under meteor showers, while Renaissance masters like Dürer embedded precise constellations into biblical scenes, merging heaven and earth with meticulous astronomy. Music, too, has always echoed the cosmos. Gustav Holst's The Planets wasn't just orchestral storytelling, it was a sonic telescope, assigning Mars the growl of brass for war, Saturn the tolling bells of time, and Neptune an eerie choir fading into silence like a spacecraft drifting beyond the solar system. Decades later, Vangelis' Cosmos soundtrack turned cosmic wonder into synthesizer waves, his melodies echoing the electromagnetic hum of interstellar space. These compositions weren't metaphors, they were attempts to sonify the universe's hidden rhythms, making the inaudible audible. Today, That tradition evolves with day personification, transforming starlight itself into music. Projects like NASA Chandra X-ray Observatory convert the vibrations of pulsars into percussive beats or map galaxy clusters' light frequencies to piano scales. The pillars of creation, those towering star-forming nebulae, become a haunting duet between harp and cello as their gas densities dictate pitch and volume. It's more than artistic whimsy. These sonic maps help scientists detect patterns invisible to the eye, like a blind astronomer reading the sky through sound. What ties these works across centuries isn't just theme, it's methodology. Van Gogh's impasto technique, layering thick paint to simulate stellar radiance, mirrors how astronomers stack exposures to reveal faint galaxies. Holst's use of unconventional harmonies parallels the dissonant frequencies of quasar jets. Even modern-day personification follows the same principle as ancient star chanters, translating cosmic phenomena into human sensory experience. The difference: today's tools, where Incas used bone flutes to mimic the Pleiades arrangement, we use algorithms to play the Milky Way's infrared glow like a galactic vinyl record. This fusion of art and science reveals something profound. Starlight doesn't just fuel discovery, it ignites creativity. The same photons that let astronomers measure a star's composition also inspire sculptors, poets, and composers. When you hear a symphony based on Kepler's exoplanet data or stand before a mural of the Hubble Deep Field, you're witnessing humanity's dual response to the cosmos: reason and wonder, calculation and awe woven together. And now, the most thrilling part. You don't need a telescope or a degree to join this conversation. With free apps like Stellarium or citizen science projects tracking variable stars, anyone can help decode the universe's oldest language. The same light that guided Polynesian navigators and dazzled Van Gogh still reaches us today, unchanged and unbroken, a bridge across time waiting for your eyes to continue the story. Standing under a clear night sky, you're not just looking at stars, you're time traveling without a telescope. That faint, fuzzy patch your eyes can barely make out. That's the Andromeda Galaxy, a staggering 2.5 million light-years away, meaning the photons hitting your retina tonight began their journey when early humans were first crafting stone tools. It's the most distant object visible to the unaided eye, a swirling city of 1 trillion stars appearing as nothing more than a smudge of ancient light. Hold up a simple pair of binoculars, and suddenly the Pleiades star cluster snaps into focus, not as a blur, but as a glittering family of blue suns whose light left during the Cretaceous period when T. Rex still ruled the planet. Finding the perfect viewing spot is half the magic. Light pollution doesn't just dim the stars, it erases them like turning up the lights during a movie. Seek out true darkness far from city glare, where the Milky Way stretches overhead like a river of crushed diamonds. Places like Cherry Springs State Park in Pennsylvania or the Atacama Desert in Chile offer skies so pristine that the Large Magellanic Cloud, a satellite galaxy of our Milky Way, becomes visible as a faint cloud to the naked eye, its light a relic from 160,000 years ago. Even in suburban backyards, patience rewards you. Let your eyes adjust for 20 minutes, and fainter stars emerge like shy guests at a party, each one a historical document written in photons. Timing matters as much as location. The winter sky gifts us with Orion, its Betelgeuse glowing orange, a star so large it could swallow Jupiter's orbit, whose light you see tonight departed around the time humans invented writing. Summer brings the summer triangle, with Vega's blue-white brilliance representing light from the dawn of agriculture. These aren't just seasonal markers, they're chapters in a cosmic biography we're all invited to read. For those craving more detail, smartphone apps like Sky Guide or Stellarium act as celestial cheat sheets, labeling constellations in real time as you point your phone skyward. But sometimes the deepest wonder comes from putting technology aside. Trace the Big Dipper's handle to Arcturus, then speed onward to Spica, an age-old stargazing trick called arcing to Arcturus that farmers used to plant crops before almanacs existed. When your finger connects these stars, you're following the same path our ancestors did, their stories written in the very constellations we share. What's breathtaking is how accessible cosmic time travel remains. Unlike fragile artifacts locked in museums, the stars demand no admission fee, just your attention. That flickering dot of Mars, it's not just a planet, it's a mirror reflecting sunlight that left when you were likely in grade school. Even moonlight is a time capsule, its silver glow showing our satellite as it was 1.3 seconds ago. Every glance upward stitches together a patchwork of eras, proving the night sky isn't just above us, it's a living archive, and we're all its curators. Now let's untangle the mysteries behind these celestial time capsules. Why does starlight take so long to reach us? Can we really see the past? And what happens when the light runs out? The answers might reshape how you see every sunset. The oldest light we can see is the cosmic microwave background, a faint glow that's been traveling for 13.8 billion years, nearly the entire age of the universe itself. This afterglow of the Big Bang fills every corner of the sky, a relic from when the cosmos was a searing plasma fog, just 380,000 years old. Today, it's cooled to barely 3 degrees above absolute zero, detectable only as static on old televisions or through specialized telescopes like Planck. Yet this whisper of heat holds the universe's baby picture, its subtle temperature variations revealing the seeds of all future galaxies. Starlight might not carry alien radio broadcasts, but it's still one of our best tools for hunting extraterrestrial life. When a planet passes in front of its star, some of that light filters through its atmosphere, picking up chemical fingerprints, oxygen and methane coexisting unnaturally. That could hint at biology, chlorofluorocarbons, or possibly industrial pollution. Telescopes like JWST are already analyzing these spectral signatures, turning starlight into a cosmic detective sniffing for clues across light years. Redshift, the stretching of light's wavelength as space expands, is nature's way of tagging starlight with a cosmic expiration date. The farther light travels, the more the universe stretches beneath it, shifting visible light into infrared or radio waves. This isn't just a curiosity, it's how Edwin Hubble proved the universe was expanding in the 1920s. Today, redshift acts like a barcode scanner for cosmic history, letting astronomers sort galaxies by age and distance without needing a single yardstick. But here's what's wild. Redshift doesn't mean light is tired or slowing down. Photons always move at light speed, it's space itself growing between us and the source, like dots on an inflating balloon drifting apart. That's why the most distant galaxies appear redshifted into invisibility. Their light hasn't vanished, it's been stretched beyond our instrument's range. Yet even this limitation tells a story, marking the horizon beyond which no signal can reach us, no matter how powerful our telescopes become. These fundamentals aren't just trivia, they're the grammar of the universe's oldest language. And the people who deciphered them, that's where the story gets even richer. From a Victorian woman mapping stellar spectra on glass plates to a radio engineer stumbling upon the Big Bang's echo, the heroes of this tale prove that cosmic breakthroughs often come from the most unexpected places. Isaac Newton wasn't just playing with prisms when he split sunlight into a rainbow. He was cracking open the universe's secret code. That simple experiment in 1666 revealed something revolutionary. white light isn't pure but a cocktail of colors, each bending at different angles. What started as a beam through a Cambridge window became the foundation of spectroscopy, the art of reading starlight's hidden messages. Fast forward 2 centuries, and a brilliant astronomer named Annie Jump Cannon would take Newton's discovery further than anyone imagined. Sitting at Harvard Observatory, she manually classified hundreds of thousands of stars by their spectra, creating a system so intuitive, Obafcom, remembered by "Oh, be a fine girl, kiss me," that it's still used today. Her work proved stars weren't random points but chemical factories with distinct life cycles, their light acting as barcodes revealing temperature and composition. Then came Edwin Hubble, the man who shattered our cosmic neighborhood's boundaries. Peering through the 100-inch Hooker telescope in 1924, he spotted a Cepheid variable star in the Andromeda Nebula, proof it wasn't a cloud within our Milky Way, but an independent galaxy millions of light-years away. Overnight, the universe expanded from a single island of stars to a vast archipelago of galaxies, each a swirling metropolis of suns. Hubble didn't stop there. By matching galaxies' redshifts to their distances, he uncovered the cosmos' most startling behavior. It's stretching like rising dough, carrying galaxies apart like raisins in an expanding loaf. But light had more secrets to spill. In the 1970s, Vera Rubin stared at galaxy rotation curves, expecting stars on the outskirts to move slower just as Pluto orbits more sluggishly than Mercury. Instead, she found stars whipping around just as fast at the edges. The only explanation, an invisible gravitational anchor, dark matter tugging at them from the shadows. Her work, initially met with skepticism, revealed that the stars we see are just the glitter on a cosmic iceberg, with 90% of the universe's mass hidden in darkness. Meanwhile, 2 radio astronomers named Arno Penzias and Robert Wilson were battling pigeon droppings on their antenna at Bell Labs. Trying to eliminate persistent microwave static, they scrubbed away nests and waste, only to realize the noise wasn't earthly interference. It was the faint afterglow of the Big Bang itself, cooled to 3 degrees above absolute zero after 13 billion years of cosmic expansion. This cosmic microwave background, as it's now known, became the smoking gun for the universe's explosive birth, its subtle temperature variations mapping the seeds of all future galaxies. These pioneers shared a common thread. They listened when light spoke. Newton heard it in a prism's rainbow, Hubble in a star's pulse, Rubin in a galaxy's unexpected spin, Penzias and Wilson in the hiss between radio stations. Their legacy lives on in every telescope pointed skyward, every spectrum analyzed, every dark matter map constructed. Yet for all they uncovered, Starlight still holds riddles that defy explanation. Why is the universe's expansion accelerating? What exactly is dark matter made of? And could the light we've yet to detect, like gravitational waves or neutrinos, carry chapters of this story we're only beginning to imagine? For all the secrets Starlight has revealed, the universe still guards its greatest mysteries like a vault. Take dark matter. We know it exists because galaxies rotate too fast and light bends around invisible mass, but after decades of searching, we still don't know what it's made of. Is it a sea of undiscovered particles, a shadow universe with its own physics? Underground labs hunt for dark matter's faint whispers, while telescopes map its gravitational fingerprints, yet it remains the cosmic equivalent of a burglar who leaves no trace but stolen stars. Then there's the universe's runaway expansion. In the late 1990s, astronomers made a jaw-dropping discovery. Not only is the cosmos expanding, but the rate is accelerating, as if some anti-gravity force, dubbed dark energy, is pushing galaxies apart. The craziest part, this dark energy makes up nearly 70% of the universe's total content. Is it Einstein's cosmological constant, woven into space itself? Or something far stranger, like a new kind of field or extra dimensions? The light from distant supernova and galaxy clusters holds clues, but every answer seems to spawn 3 new questions. And what about the cosmic dark ages? After the Big Bang's glow faded but before the first stars ignited, the universe was a pitch-black sea of hydrogen. How did those pioneer stars' population 3 form without heavier elements to cool collapsing gas clouds? Simulations suggest they were monsters, hundreds of times the sun's mass, burning bright and dying young. Yet we've never directly observed one. Their light, stretched by cosmic expansion into infrared oblivion, might still be traveling toward us, waiting for telescopes like the James Webb Space Telescope to catch their faint afterglow. Even the cosmic microwave background, our most pristine snapshot of the early universe, hides riddles. Why does one hemisphere appear slightly warmer than the other? Could this axis of evil hint at a pre-Big Bang universe? And what about the mysterious cold spot, a vast, unexplained region where the background radiation dips unexpectedly? Some theories suggest it's a bruise from a collision with another universe, while others blame cosmic voids. Either way, these anomalies whisper that our standard model of cosmology might be missing a chapter. The most thrilling possibility, future telescopes could uncover mysteries we haven't even thought to ask. When Galileo first pointed his spyglass at Jupiter, he didn't set out to discover moons, he was just curious. Similarly, projects like the Vera Rubin Observatory or the European Space Agency's Euclid mission might stumble upon cosmic phenomena that rewrite physics textbooks. Maybe they'll catch the first signs of wormholes, detect echoes from a cyclic universe, or find galaxies too ancient to exist under current theories. Here's the beautiful part. You don't need a PhD to join this cosmic detective work. Citizen science projects like Galaxy Zoo let anyone classify galaxies from telescope images, while apps like Zooniverse offer stargazing challenges where amateurs have spotted everything from supernova to interstellar comets. Even your smartphone can contribute. Projects like Dark Sky Meter use its camera to measure light pollution, helping scientists preserve our view of the stars. The universe's oldest light hasn't stopped telling its story, and now, more than ever, it's inviting everyone to listen. You don't need a fancy degree or $1 million telescope to start decoding the universe's oldest messages, just an internet connection and a dash of curiosity. Platforms like Zooniverse throw open the doors to cosmic discovery, letting anyone with a screen help classify galaxies, hunt for exploding stars, or even track interstellar dust clouds. Picture this: while sipping your morning coffee, you might scroll through images from the Hubble Space Telescope and spot a never-before-seen galaxy merger, something even professional astronomers could have missed. That's exactly what happened to Hanny van Arkel, a school teacher who discovered a bizarre green cosmic blob now named in her honor. But the adventure doesn't stop online. Local astronomy clubs are treasure troves of hands-on learning, where seasoned stargazers love sharing their knowledge and telescopes. Many host star parties in parks or on rooftops, turning the night sky into a communal classroom. Imagine peering through a telescope at Saturn's rings for the first time, or watching a meteor shower with a group of enthusiasts who can point out constellations like old friends. Even public libraries and schools frequently organize stargazing nights, often with gear provided, no experience required. For those craving deeper dives, free online courses from universities like Yale or Edinburgh break down complex topics like spectroscopy into bite-sized lessons. Ever wondered how astronomers know what stars are made of? These courses teach you to read the chemical fingerprints hidden in starlight, just like the pros. Apps like Sky Safari or Stellarium turn your smartphone into a portable planetarium, identifying stars and planets overhead in real time. The beauty of these projects. They prove that cosmic exploration isn't reserved for labs or elite institutions. When you join a citizen science initiative or attend a local star party, you're stepping into a tradition that stretches back to Babylonian sky watchers and Polynesian navigators, people who mapped the heavens with nothing but patience and naked eyes. Today's tools just let us see further, dig deeper, and connect faster. So why does ancient starlight still captivate us? Because every photon is a time traveler. That flicker from Sirius, an 8-year-old postcard from Earth's celestial neighbor, the Andromeda Galaxy's glow, a 2.5 million-year-old snapshot from when humanity's ancestors were crafting their first tools. Unlike fossils or ruins, starlight doesn't decay. It just keeps coming, an endless stream of cosmic history waiting to be unpacked. Whether you're classifying galaxies from your couch or sketching the moon through a borrowed telescope, you're not just observing the past. You're touching it. Starlight is more than just illumination. It's the universe's oldest historian, its most patient messenger. Every photon that reaches us, whether from the cosmic microwave background's faint whisper or a quasar's brilliant scream, carries chapters of a story written across billions of years. Think of these beams of light as cosmic archivists, meticulously recording the universe's growth from a searing plasma to the glittering web of galaxies we see today. The CMB's subtle temperature variations, those are the gravitational blueprints for all structure, imprinted when the cosmos was barely 380,000 years old. Quasar spectra, their chemical diaries, preserving the composition of gas clouds that existed before Earth formed. Even the distortion of starlight around galaxy clusters isn't just pretty, it's dark matter signing its name in the margins of space-time. What's breathtaking is how interconnected these cosmic records are. The same expansion that stretched the CMB's light into microwaves also redshifted the earliest starlight into infrared oblivion, forcing us to build telescopes like JWST to recover those lost chapters. Gravitational lensing, the bending of light around massive objects, doesn't just reveal dark matter's distribution. It magnifies galaxies too distant to see otherwise, acting as nature's own zoom lens. And those supernovae whose dimming revealed dark energy, their light is the same color-changing beacon that lets us measure the universe's expansion rate at different epochs, like mile markers on a cosmic freeway. This celestial detective work reshapes how we see our place in the cosmos. The iron in your blood, the calcium in your bones, these elements were forged in stellar explosions whose light may have faded eons ago, yet their physical legacy lives on in you. When you gaze at the Andromeda Galaxy, you're not just seeing 2.5 million years into the past, you're looking at a future collision partner, a reminder that even galaxies aren't static exhibits but dynamic players in an evolving universe. The photons hitting your retina from Orion's belt began their journey when early humans were discovering fire, making stargazing the closest thing we have to a shared experience across millennia. Yet for all we've decoded, the universe still holds mysteries written in light we can't yet read. The polarization patterns in the CMB might conceal evidence of cosmic inflation's violent birth pangs. Faint infrared glows between galaxies could trace the cosmic web's hidden rivers of gas, and the gravitational waves rippling through space-time, themselves a form of light, just at wavelengths we can't see, may carry stories of black hole collisions from the universe's first seconds. Every answer starlight provides seems to uncover 3 new questions, ensuring the conversation between humanity and the cosmos never grows stale. So the next time you step outside under a clear night sky, remember, you're not just looking up. You're peering backward through time, touching the universe's history with your own eyes. Those stars overhead aren't just points of light. They're the last echoes of events that shaped everything from atoms to galaxies, a luminous bridge between our fleeting moment and the cosmos' grand sweep. And with every telescope we build, every spectrum we analyze, we're not just passive observers. We're active participants in the universe's oldest conversation, learning to listen more deeply to the light that's been speaking since the dawn of time. Standing beneath the vast canopy of the night sky, it's easy to feel small, a fleeting speck in a universe measured in billions of years and light years. Yet here's the paradox: that same human mind feeling insignificant is the only known entity in the cosmos capable of tracing starlight back to the Big Bang, measuring the spin of black holes, and decoding the chemical recipes of distant suns. We are both ephemeral and extraordinary, creatures who emerged in the universe's final cosmic moments, but can reconstruct its entire history from the light that reaches us. Consider this: every time you look at Orion's belt, you're seeing stars whose light began its journey around the time humans first domesticated fire. The photons striking your retina tonight have traveled through centuries, carrying stories from an era when woolly mammoths still roamed. And when telescopes like Hubble or Webb capture light from galaxies 13 billion light-years away, they're not just collecting data. They're resurrecting moments when the universe was in its infancy, long before atoms like those in your body even existed. This ability to peer across time and space isn't just scientific progress, it's a form of cosmic time travel, achieved not with machines but with curiosity and mathematics. What's even more astonishing is how recent this understanding is. A mere 5 centuries ago, we believed the stars were fixed to a celestial sphere just beyond the planets. Today, we know they're distant suns, some with planets of their own, and that their light carries fingerprints of elements forged in stellar furnaces. The very atoms that make up your hands, the carbon, oxygen, and iron, were once stardust scattered across the galaxy by supernovae before gravity gathered them into Earth and eventually you. In that sense, starlight isn't just something we observe, it's something we're made of. This knowledge shouldn't overwhelm, it should awaken something primal. When ancient cultures told stories about constellations, they weren't just explaining the night sky, they were finding their place within it. Modern science hasn't erased that need for connection, it's deepened it. Now we know that the same physical laws governing star formation also shape the neurons firing in your brain as you read these words. The universe isn't just around us, it's within us, a thread woven through every cell and thought. So tonight, step outside, let your eyes adjust to the darkness. Whether you're gazing at the Milky Way from a mountaintop or spotting a single star through city lights, remember, you're not just a passive observer. You're the universe's way of knowing itself, a conscious node in a vast network of light and time. Those photons have crossed unimaginable distances to meet your eyes, completing journeys that began before mountains rose or oceans formed. And when you share what you see, whether with a friend, a child, or a community of fellow explorers, you're adding another voice to humanity's ongoing conversation with the cosmos. The stars have been speaking for billions of years. We've only just begun to listen. What they've taught us so far is this: we may be small, but we are not strangers here. The light that guides us is the same light that made us, and in its glow we find not just answers, but endless new questions waiting to be asked.